Hello everyone, this is Edward from EDEXCEL. Welcome back to another lecture on analytical chemistry. Today we are going to be looking at the introduction to NMR spectroscopy. NMR spectroscopy basically is used to identify the carbon to hydrogen frameworks of organic compounds, and it is usually used hand in hand with infrared spectroscopy. Now, after using infrared spectroscopy to identify the fingerprint of compound or identify the compound, you then use NMR spectroscopy to identify the carbon to hydrogen frameworks, and that will help to confirm the organic compound. Okay. Now, NMR spectroscopy is applicable to some certain nuclei, and they are applicable to nuclei that have a state called spin state. For a nuclei to have a spin state, it's either it has an odd number of protons or odd number of neutrons. Okay. Now, example of such, we have hydrogen, proton. We also have carbon 13. We have nitrogen 15. We have fluorine 19. We have phosphorus 31. Okay, so now all these nucleus, right, they have a spin state. Now let's look at hydrogen proton for example. Now hydrogen has just one proton, all right, and we know that it has a spin state. Okay, and in physics class we understand that any object or any material that is charged and it's moving possess what we call electromagnetic property. Okay, it becomes electromagnetic, right? Now let's say we have so many protons of this hydrogen. Okay, now they possess electromagnetic property, but their direction of the magnetic field are randomly. Okay, random magnetic field. Now, when these protons are placed in an external magnetic field, okay, let's call that external magnetic field B naught. Now, this B naught has a direction. Now, some of them will align with the direction of the external magnetic field, while some of them will align opposite the direction of the magnetic field. Okay, now those that align in the same direction of magnetic field, we call them, instead of they're in alpha state. Okay, so some of them will be aligning this way, while some of them will be aligning opposite direction of the magnetic field. Okay, and we call that state the beta state. Now the thing is this: in reality, most of these protons will prefer to align with the same direction of the external magnetic field. Let's use this analogy for example. If you are trying to swim across a river, where will it be easier for you? Is it when you are swimming in the same direction of the river, or when you are swimming opposite direction of the flow of the river? I believe swimming in the same direction of the flow of the river will be much easier. So the same thing is applicable here. So most of these protons prefer to align the same direction of the with the same direction of the external magnetic field B naught. However, you still find some of them aligning opposite direction. Okay, so now the difference between the alpha state and the beta state is called the delta E. Okay, and there is a direct relationship between delta E and P naught, which is the external magnetic field. Delta E is directly proportional to B naught, which means if you increase the external magnetic field, the energy difference between the alpha state and the beta state will also increase. Now, these protons can actually switch from one spin state, the alpha spin state, to the beta spin state. They can actually switch. Now, what does it take for an alpha spin state proton to switch to a beta spin state proton? Now, it takes what is called radio frequency. Now, when you apply a radio frequency, RF, okay, now the alpha spin state would switch to a beta spin state. Okay, now this beta spin state, when it loses radio frequency, it also switch back to an alpha spin state. Okay, so you apply radio frequency for alpha spin state to switch to beta spin state, and when the beta spin state loses radio frequency, okay, so when it loses energy, rather, when it loses energy, it goes back to an alpha spin state, and while doing that, it emits radio frequency as well. So now the front and back of this process is what they call a resonance. Okay, the continuous switching of the state of these protons is what they call resonance, and that is where the name comes from, nuclear magnetic resonance spectroscopy. I hope that makes sense. Now we can calculate the energy difference between the spin state, okay, the alpha spin state and the beta spin state. Using this formula, the energy delta E will be equal to Planck constant times the frequency. So this is basically the frequency of the energy which you are applying to change the state from one state to another, from alpha to beta spin state. Okay, and frequency, this frequency V is equal to gyromagnetic ratio divided by 2 pi multiplied by the strength of the external magnetic field. So we have our delta E then to be equal to H, the Planck constant, multiplied by gyromagnetic ratio divided by 2 pi, then times the external magnetic field. Okay, and as you can see from this equation, the delta E is directly proportional to the strength of the magnetic field. Now, I know you'll be wondering, what is this gyromagnetic ratio? The proton nuclei has a gyromagnetic ratio of 2.675 times 10 raised to the power 8 per Tesla per second. While that of carbon-13 is 6.688 times 10 raised to the power 7 per Tesla per second. So this is how to calculate the energy difference between the alpha spin state and the beta spin state. In some cases, you may also be asked to calculate the frequency. Okay, so if you ask to calculate the frequency, you make use of these equation. So let's look at the example. What is the operating frequency required of a NMR spectrometer to generate a magnetic field of 15.56 Tesla? And so, to answer this question, we use the formula. You are calculating the frequency. You use the formula nu. Okay, is equal to gyromagnetic ratio divided by 2 pi multiply by the external magnetic field. All right, and now the question is what would be your gyromagnetic ratio? Okay, we have that our B naught is equal to 15.56 Tesla. What is our gyromagnetic ratio? What is the value of our gyromagnetic ratio? And the answer lies in the question. As you can see from the question here, it says, what is the operating frequency required of a HNMR? That is a proton NMR. And the value for the gyromagnetic ratio of proton NMR is, so we have 2.675 times 10 to the power 8 per Tesla per second. So we put this value into the equation. Our nu will be equal to 2.675 times 10 to the power 8 divided by 2 times 3.142, all multiplied by 15.56, and that will give us, and that is equal to 662.36473.5.8 Hertz. So approximately we're having 662 megahertz. I hope that makes sense. So this is just the basic introduction. We'll be gradually moving into the more complex aspect of NMR spectroscopy. So in our next lesson, we're going to look at the number of signals, how to determine the number of signals produced or that we produce in NMR spectroscopy. See you some other time.